In 1963, the Atlantic Ocean off Iceland's southern coast began to boil. Fishermen watched columns of dark smoke and ash rise from the surface of the water, and within hours, a new island was being born from the seafloor. This was not a gentle process. This was an underwater volcano tearing through the ocean itself, and the consequences would alter the chemistry, biology, and circulation of the surrounding waters for decades. The eruption site sat along the mid-Atlantic ridge, the submarine mountain chain where tectonic plates pull apart and magma rises to fill the gap. Here, at a depth of roughly 130 meters beneath the waves, molten rock had been building pressure. When it finally broke through, the explosion sent material skyward with such force that an entirely new landmass, Surtsey, emerged above sea level within days. But the island was only the visible symptom. Beneath the surface, something far larger was happening to the ocean around it. The seafloor was not merely cracking open, it was rewriting the conditions under which an entire marine region functioned. Consider the environment. The North Atlantic in this region is cold, nutrient-rich, and home to some of the most productive marine ecosystems on Earth. Water temperatures hover near 4 to 6 degrees Celsius at depth. Currents carry oxygen and dissolved minerals along well-established paths. Marine life, from plankton to fish to seabirds, depends on the stability of these conditions. An underwater volcanic eruption of this magnitude introduces a violent disruption to every one of those parameters simultaneously. The ocean here is not empty space. It is a densely interconnected system where a change in one variable cascades through everything else. When magma meets seawater, the interaction is catastrophic and immediate. Temperatures at the eruption point exceed 1,000 degrees Celsius. The surrounding water flash heats. Dissolved gases, primarily sulfur dioxide and carbon dioxide, pour into the water column in enormous quantities. Mineral-rich particles cloud the area for kilometers. The pH of nearby water shifts toward acidity. Thermal plumes rise, dragging deep water upward and displacing the natural stratification that marine organisms rely upon. The physics of this collision between molten rock and cold seawater produces shockwaves of change that radiate outward from the eruption site in concentric rings of diminishing intensity. What researchers documented in the waters around Surtsey during and after the eruption revealed a cascade of biological consequences. The immediate vicinity became a dead zone. Fish populations fled. Plankton communities collapsed in the superheated, acidified water closest to the vent. But further out, something unexpected occurred. The massive injection of iron and other trace minerals into the surrounding ocean acted as a fertilizer. Phytoplankton blooms appeared in areas that had previously been mineral-limited. The eruption was simultaneously destroying life in one zone and stimulating it in another. This paradox, death at the center and abundance at the margins, defined the biological signature of the event. The instruments available in the early 1960s were limited by modern standards. Researchers relied on water sampling from ships, basic temperature probes, and visual observation. Satellite ocean color imaging did not yet exist. Continuous monitoring of dissolved gas concentrations, real-time pH measurement at depth, and high-resolution bathymetric mapping were all decades away. What scientists could measure, they measured carefully. But the full spatial extent of the chemical changes, the depth to which thermal effects penetrated, and the precise timeline of biological recovery remained partially beyond their observational capacity. The tools shaped the picture, and the tools were incomplete. This is a critical limitation in the evidence. We know the eruption altered ocean chemistry. We know biological communities were disrupted and then reorganized. But the exact boundaries, the precise concentrations of dissolved volcanic gases at various distances, the complete picture of how currents redistributed that altered water. these details remain incompletely resolved. Later expeditions revisited the site with better technology, but by then, years had passed and the ocean had already begun its long process of recovery and rebalancing. The sharpest chemical signals had dissipated. What remained were indirect markers and biological succession patterns that told a story in retrospect rather than in real time. Several explanations exist for how a single submarine eruption can alter waters on a regional scale. The first and most directly supported is thermal disruption. Volcanic heat changes water density, which changes how layers mix, which changes where nutrients concentrate. The second is chemical injection. Sulfur compounds, iron, manganese, and carbon dioxide dissolve into seawater and shift its fundamental chemistry. The third is particulate loading. Volcanic ash andite minerals suspended in the water column block light, change turbidity, and physically smother benthic organisms on the seafloor. Each of these mechanisms is well documented in volcanic oceanography. What made the Surtsey event remarkable was the scale at which all three operated simultaneously in a biologically rich region. The best current explanation, supported by decades of follow-up research, is that submarine volcanic eruptions function as ocean-scale reset events. They do not simply kill what lives nearby. They restructure the chemical and thermal environment in ways that favor entirely different communities of organisms. The waters around Surtsey did not return to their pre-eruption state. They evolved into something new. Pioneer species colonized first. Nutrient dynamics shifted. The ecosystem that eventually stabilized was related to but distinct from what had existed before. The eruption did not merely damage a system. It ended one arrangement and initiated another. The ocean covers approximately 70% of Earth's surface. It contains 97% of all water on the planet. It functions as an enormous reservoir of heat, as a primary driver of climate and weather patterns, and as the origin point of atmospheric oxygen through photosynthesis. It harbors most of Earth's animal and protist life. Within this vast system, volcanic forces operate continuously along the mid-ocean ridges that encircle the globe. And yet, a single volcanic event beneath its surface can reorganize the chemistry of an entire region, redirect biological communities, and leave a signature that persists for generations. The unresolved question is not whether submarine eruptions change oceans. That is established. The question is how many such events occur undetected along the more than 65,000 kilometers of mid-ocean ridges, and what their cumulative effect is on global ocean chemistry over time. Our monitoring coverage of the deep sea floor remains sparse. Most of what happens at volcanic sites along these ridges goes unwitnessed and unmeasured. We detect the largest events. We miss an unknown number of smaller ones. The gap between what we observe and what actually occurs remains one of the defining uncertainties of ocean science. Every instrument we lower into the deep ocean measures a tiny fraction of an enormous system. Every expedition covers a small patch of seafloor for a limited time. The ocean is not merely large, it is large enough that volcanic eruptions capable of altering regional chemistry can occur, run their full course, and leave only indirect evidence by the time we arrive to look. Surtsey was visible because it broke the surface. It announced itself with smoke and ash and a new island. But beneath the waves, along those tens of thousands of kilometers of ridges, the seafloor continues to split, magma continues to rise, and the ocean continues to change in ways we have not yet learned to fully observe. What we measured at Surtsey was not the exception. It was the exception we could see. Somewhere along those ridges right now, the ocean floor is likely doing it again. And we are not watching.